Welcome back. This is Mr. Hassan's Maths channel, and I'm now going to answer question number 3 from the June 2019 International A-Level Edexcel Mechanics M1 paper. This question here is about moments, and here the question is about a beam AB which has a mass of 100 kilograms and a length of 8 meters. The beam is held in equilibrium and it's in a horizontal position by two vertical ropes attached to the beam at C and D. So the beam and the ropes are perpendicular to each other. The beam is horizontal and in equilibrium. It says AC is 0.5 meters, as is BD. The gymnast, or there is a gymnast of mass M kilograms standing on the beam at the point P, where AP is 2 meters, as shown in figure 2. The beam remains horizontal and in equilibrium. The tension in the rope attached to the beam at D is 637 newtons. So there's a tension in this rope, 637 newtons. The gymnast is modeled as a particle, the beam as a uniform rod, and the ropes as light inextensible strings. It says find the value of M and the tension in the rope attached to the beam at C. Okay, so I've got a copy of the diagram down here so I can put in all the values we need. Now the first thing we're going to focus on is the fact they told us the mass is 100 kilograms, and they also told us that it's a uniform rod. Okay, that will help us to draw the force, the weight acting on the beam. The weight of the beam, okay, which is the force of gravity acting on the beam, is going to be exactly halfway along its geometric center. So this is where the weight will act. Exactly halfway along its geometric center, and they told us the mass of the beam is 100 kilograms, so this is going to be 100 G newtons. The force is 100 G newtons. That's the weight of the beam, the force of gravity acting on the beam. Okay, so that's one thing. Then it tells us also that there's a gymnast of mass M kilograms standing on the beam at the point P. So the other thing that's acting on the beam is the weight of the gymnast, which is acting on the beam at the point P. Okay, again, vertically downwards. And here we don't know the mass of the gymnast, so it's mg newtons. That's the force, the weight of the gymnast acting on the beam. Okay, that's mg newtons. Then we also have the tension in the rope attached to the beam at D is 637 newtons. So there's a tension here, which we know its value. That tension is 637 newtons at D. And there's also a tension at C, which we don't know, and we have to find. Okay, so that's the tension acting at C. I'll just call it T. All right. So those are all the different things we know about this particle, all the forces acting on it. So the forces acting on the beam are what we're concerned with. So some people will say, sir, what about the reaction force of the beam on the gymnast at this point P? We are not considering the forces acting on the gymnast. Here we're considering the forces acting on the beam alone. We're considering only the forces acting on the beam. There's also a tension in the string acting downwards as well. But we're not considering that. We're only considering the forces acting on the beam. And that's the tension on the string pulling upwards. Okay, so we're considering only the forces acting on the beam itself. No, not the forces that the beam is exerting on anything else. All right, so that's why we only consider, we don't put reaction force here as well. No, we keep the force of the forces acting on the beam alone. All right, so now what we're going to do now is we're going to try to find the value of M and the value of T. There are two unknowns here. So for example, if I decided, let's take moments about A, for example. Okay, I will end up with two things that I don't know. You'll have 0.5 times T, and you have 2 times mg, and these two we'll be able to work out the moments, but there'll be two things that we don't know. So that will make life a bit more difficult. We could counter that by taking moments about another point like B, and then have two equations with M and T in it, but that's a bit more hassle than doing something which makes life a lot easier, which is taking moments about a point, okay, which will cause us to eliminate one of the unknowns. So for example, if I take moments about C, okay, then the moment of T the force T about C is 0, because the moment is the force times its perpendicular distance from the point that you're taking moments about, and this is on C, so the moment of T on C will be 0. So taking moments about C is going to help us eliminate T and leave us with one unknown. So I'm going to take moments about the point C. So if I take moments about the point C, I've got to think of all the distances in relation to C. So what I'm going to do here is I'm going to think about what these distances are in relation to C. So for example, the distance of the weight of the gymnast from the point C, well, that's 2 meters, that's 0.5 meters, so that's 1.5 meters there. And also from C to the weight acting, well, we know that that's 4 meters because it's exactly halfway along, as we mentioned, and that's 0.5 meters, so that's going to be 3.5 meters. And we also have this distance of this tension at D, that distance there, well, this is 0.5 meters, this 0.5 meters, that's 1 meter. Take away from 8, that's 7 meters, so that length is 7 meters, so that force is acting 7 meters away from C. So now we have the distances of all the forces acting from C, so we can take moments about C. Let's look at the clockwise moments first. The clockwise moments are going to be mg times 1.5, okay, and then you're going to have plus 100g times, and that's 3.5, and that's equal to the anti-clockwise moments because it's an equilibrium. That's going to be 637 times 7. Okay, so that will help us find what m is. Okay, so what I'm going to do is, so this gives me 1.5 mg plus, that's going to be 350 g equals 637 times 7. So 637 multiplied by 7 gives us 4,459. So now I need to find what m is, so I can subtract 350g from both sides, 350g, and divide by 1.5g. Okay, so my m is going to be given by, so we know that g is 9.8, so I'll just do this. So 4,459 minus 350 times 9.8 divided by 1.5 times 9.8, and that gives us 70. So m is equal to 70 kilograms. So m is 70 basically. Okay, so m is 70 because the unit is already there. M kilograms, right? Yeah, so we'll just say m is 70. You don't have to mention the kilograms because it's already given in that unit. So m is equal to 70, and there's the answer to that's the answer to part 1. That's the value of m. Okay, so that's the value of m, so that's for part 1. And then part 2 says we got to find the value of the tension at C. So we got to find this T. Now, once we found what m is, we can find what T is very easily. We could take moments about another point if we wanted to, and that would be perfectly fine. However, what will be easier here is you can just use the fact that this is an equilibrium, so the forces acting up and down balance each other out. So we can say T, which we have to find, plus 637 is equal to mg, which we know now know m is 70, so it's 70 times g plus 100g. Okay, that's 70 plus 100g, so 170g. So we can say T is going to be 170 times g minus 637. So therefore T is equal to, so we can take 170 multiplied by 9.8, take away 637. That gives us 1,029 newtons. Okay, now 1,029 newtons. Now, what we can do with this is, because we used G, we can write our answer to 3SF or 2SF. Okay, so you should either give it to 3SF or 2SF. If it's 2SF, okay, then we'll write it as we'll stop there. So it'll either be 1,000 newtons. If it's 3SF, it'll be 1,030 newtons. So the answer should be given either to 2SF or 3SF. Both of those will be accepted. It's best not to leave it in terms of this value, because this is a rounded value, because we've used G. We haven't used G in its exact value. We've used G rounded as 9.8, as we're asked to do, to two significant figures. So that's why, the answer should really be in two significant figures, which will be 1,000 newtons. But if you write it to 3SF, that's also acceptable. Okay, whenever you use G in your calculation, then writing your answer to 2SF, your final answer to 2SF, is what really you should do. But they do accept 3SF, and that's normally the safest thing to do, because when you don't use G, it should be to 3SF. So that's something that you could take into account here. So both of those answers would be acceptable for this part 2. Okay, part 1, it already came out as 70 exactly. So it's 2SF, 3SF, whatever. It doesn't really make any difference here. That's fine. All right, question number part B. It says, state how you have used the fact that the beam is modeled as a rod. Okay, so basically we assumed that the rod, when it's a rod, we assumed that it didn't bend or buckle. It didn't bend or buckle. It remained straight. Okay, it remained straight. Okay, that's what we assumed when it says it is a rod. Remained straight. Okay, so something like that, mentioning it doesn't bend or buckle, would be sufficient for part B. So there's the answer to part B. Now we're going to go on to part C. Now it says, the gymnast at P now gets off the beam and is replaced by two gymnasts. One gymnast of mass 60 kilograms stands on the beam at P, and the other one of mass 48 kilograms stands on the beam at X, where AX equals X meters. The beam remains horizontal and in equilibrium, but the tensions in the two ropes are now equal. The two gymnasts are modeled as particles. So now we've got a new situation. You have a gymnast at P. Let me just change that. A gymnast at P who has a weight of 60 kilograms. So that's 60 G newtons there. Then you have a gymnast somewhere else. We don't know where that is, but it's somewhere. We're going to call it X. We know that the distance of X from A, the distance of X from A is basically that distance there is X meters. We don't know the exact distance. From A is X meters. Okay, that's what we're told. And there's another gymnast over here. Okay, but this gymnast has a mass, which is less. The mass is how much? It should be acting vertically down. Straighten that up a bit. The mass of this gymnast is 48 kilograms. So that's 48 G newtons acting down here. We know that the weight of the beam is still the same. It's 100 G newtons acting. Is that straight or not? I don't think it's straight, is it? Let's make sure. That is straight, that's fine. Okay, so that's acting down. That's 100 G newtons acting straight down there. That's the weight of the beam. Okay, and then it tells that the tension of the two ropes is equal. So of course the tensions are not the same as before, because the situation has changed now, of course. But the tensions of the two ropes are now the same. So this second gymnast is starting at X such that, the tension in the two ropes will be equal to each other. So we're going to just call that distance X. And what I'm going to do is I'm going to take moments about A to try and help us find what we're looking for, which is the distance X. Okay, so we're going to find the value of X. All right, that's what part C says. Okay, find the value of X. So what I'm going to do here is I'm going to take moments about A first, and let's see how that will help us. There will be two unknowns here, but we can work out those other unknowns. In fact, you know what I'll do first? I'll work out what T is. Let's first find what T is, because that will help us, because we can work out what t is because both these t's are the same t, so they're like terms. And we can, first of all, let's do this first. Let's take the upwards, this is an equilibrium, so the upward forces and downward forces are equal. So we have the upwards forces, which are t plus t, which is 2t, is equal to the sum of all these forces, which is 60g plus 100g plus 48g. So we can say 2t is equal to, that's 160, that's 208g. So therefore we can say the tension in each of the strings is 104 G newtons. Okay, so once we've figured that out, we can then have just one unknown, which is the x. So we figured out what these t's are, so I can just replace them with 104 G newtons. Okay, that's also 104 G newtons. So now we can take moments about A. Why am I taking moments about A? I can take moments about anywhere I want to. But I want to take moments about A because the distance we're trying to find is the distance from A to X. So that will just give me my answer straight away. I mean, if I wanted to eliminate one of these forces to make life easier, I could take moments about, say, C, or even about this point, or any point I want to eliminate one force at least. I'll still get the same answer, but then I'd have to work out the distance X in relation to the distance I found for the moments I've taken. So I'm going to just take about A, then my X will be my answer. That's just, I prefer to do that. So if I take moments about A, the clockwise moments are, now we've got to think about these distances. I'm just going to write these distances in. As we're taking moments about A, it makes life just a little bit easier. So I know that this is already marked as 2 meters. This is already marked as 0.5 meters. This is the distance of 4 meters because it is halfway along, and the distance from here to here, the distance from there to there, up to that weight there, is again X. In fact, I've already marked that as X, so I don't even need that one either. Okay, and that distance, the one we need, I guess, is this distance over here, that distance over there. That distance is 8 minus 0.5, that's 7.5 meters. 7.5, it looks like 7.6, doesn't it? 7.5 meters from A. Okay, so we have all the distance we need. So let's look at the clockwise moments, which are these three. So we have 60g times 2 plus 100g times 4, not 8, 4, half of 8. Okay, so that's times 4 plus 48g times x. Okay, that's that moment of that force, of that what we're trying to find, x. And then the anti-clockwise moments for A are going to be the two tensions. So it's going to be 0.5 times 104g plus, and that's 7.5 times 104g. Okay, those are the anti-clockwise moments, and they're equal to each other. So now we're going to have something, well, we can get rid of all the g's. If every term has a g in it, so we can divide both sides by g to get rid of that. So we've got 60 times 2, which is 120, plus 400 plus 48x is equal to a half of 104. Well, I'll just put that in my calculator, the whole thing. So you have 0.5 times 104 plus 7.5 times 104, which is basically the same as 8 times 104. Anyway, that's going to give you, and that's we've got rid of the g's, yes, so that's 832. Okay, so now we're going to have that's going to be 48x is equal to 832 minus 520. That's minus 520. That gives us 312. So 48x equals 312. So x equals 312 divided by 48, which gives us 6.5. So x is equal to 6.5 meters. And there's the answer. 6.5 meters from A. And that's the value of x. So there we have the answer to this question on moments. I hope that was clear. Thank you for watching. Other questions which are from this particular paper can be found by looking at the playlist that will be over here. That's from this June 2019 Mechanics M1 International A-Level paper. Other questions from the topic of moments can be found in this playlist over here. You You can subscribe to my channel by clicking on this link. Thank you for watching and see you soon.